Hello everyone, this is Worksheet 6.2, the thermodynamic square. Now if you remember in class, I told you about the total differentials of the various thermodynamic functions, including internal energy, enthalpy, and the Gibbs and Helmholtz free energies. And you expressed some confusion about how you would construct those total differentials. And then later I told you about the Maxwell relations, and you were asking if there's any easy ways to get those. And I told you that the way that I would do it is to start from the internal energy and use a Legendre transform and then partial differentials in order to get it. But maybe that's not the best way for everyone, and so I wanted to introduce you to an idea that I don't use on a regular basis. I don't know, maybe I should, but Dr. Martin uses this technique when he does thermodynamics, and so maybe it would be useful to know. Now the way this works is that we use a mnemonic, and what the mnemonic is that we say good professors have studied under very ambitious teachers. All right, and we use the first letter of this mnemonic to construct the thermodynamic square. And so let me show you how you do that. You start down here at the very bottom side of the square, and we put in G for good. Professors have studied under very ambitious teachers. And then the last step is to put a negative sign on this side of the square. All right, now what's nice about this is that if you identify a particular thermodynamic variable that you're interested in, like say we just choose G, then its natural variables are just right there next to it. And so it becomes a lot easier for us to construct our total differential because we can just put dp right there and then also a dt, because that's the other natural variable of G. And then what's going to be the coefficient? The coefficient of each of the natural variables is going to be on the opposite corner of the thermodynamic square. And so since V is on the opposite corner of P, we can put V right there. And then S is on the opposite corner of T, and it's actually negative in this case. So we get a negative S dt. And so this just becomes V dP minus S dt. Notice that when I put P into my differential, I did not include the negative sign, but I did include the negative sign when I did it for the coefficient over there. So that's an important distinction that you should make sure to remember. All right, let's go ahead and try another one. Good professors have studied under very ambitious teachers. And, let's choose U. Why not? du, we've got the natural variables right next to it. So this is going to equal ds and dv. And I'm forgetting my negative signs here. The opposite corner of v is going to be negative p, so then my negative p goes out right there. And the opposite corner of s is going to be t, positive t, and so that goes right there. And that's it. That is the total differential of u, and you could do this for either of the other functions if you want to as well. Not as if the... All right, on this side of the sheet, I'm going to show you how to use the thermodynamic square to get the Maxwell relations. So we'll start with our mnemonic again. Good professors have studied under very ambitious teachers. Don't forget the negative signs there. And the way that we get a Maxwell relation is we sort of construct a U-shaped object facing some particular direction here inside the thermodynamic square. We've got the tips of the U-shaped object, and we've got the corners as well. And the way it works is that you would put each of the tips, the variables on the tips of this U, at the top of the numerator of your Maxwell relation. So we would get dp, and then over here dt, and then what goes on the bottom are going to be the variables that are in the corner there. And since p and s are connected, then we get a ds, and then t and v are connected, so we get a dv. Hopefully you kind of see how that works. We sort of make a U shape going like this, and then the Maxwell relation becomes sort of a U shape going like this, if that makes sense. Now there's a couple other things that we've got to do. We have to worry about the negative signs. And the trick that I've found for knowing whether to include a negative sign or not is if the tips of that U-shaped object, if one of the tips is in one of these variables that has a negative sign, and since that one is in P, this side gets a negative. So I'm going to rewrite this now. This is going to become negative dp ds equals positive dt dv. Well, what about the variables we hold constant? It's just going to be the opposite variable that we hold constant. So since this side is a derivative with respect to s, and this side is a derivative with respect to v, we just make the opposite variables held constant for each one of those. And that's it. That's one Maxwell relation. I'm going to show you how to do a couple more here just so that you feel a little more comfortable to give it a try yourself. Good professors have studied under very ambitious teachers. Negative signs there. Let's make a U-shaped object going this way. What the heck? All right, so that's going to turn out to be dv ds equals dt dp, because remember we're going in the order, in this order like that, with that U-shaped object. And there's no negative sign because neither of my tips are in a square that has a negative sign. And so then I have to hold the opposite variable constant, so that gets p held constant, this gets s held constant. I should also point out that it's possible to flip these around. So what you might see is ds dv at constant p equals dp dt at constant s. You could very well see that too. That's possible. All right, let's go ahead and try one more. Good professors have studied under very ambitious teachers. And let's make a U-shaped object going this way. Got my negative signs there. This becomes ds dv equals dt dp. And both sides, both of these have negative signs, so I can put negatives there, or just leave them out because that just algebraically cancels out. And then I'll put the opposite variables as what's in the denominator held constant. And that's it. Hopefully you may find this technique useful for when you're taking your exams and doing your homework and so on and so forth.